Okay, let's get going. Welcome back. This is the 9th lecture of the Condensed Matter course. A couple quick things. First of all, the videos from the lectures, they're starting to appear online. You can get to them. They're linked from my webpage if you want to try them out, watch them again if you find it's useful. Let me know if you have any trouble with the technology. We're still troubleshooting some things. Also, the message board, so far people haven't used it all that much. Please don't be shy. I promise you'll find it helpful. So at this point, we're about a third the way through the course, so it's worth sort of stopping for a second and taking stock of where we are and where we've been and where we're going. So far, we've really been looking at trying to build up some sort of microscopic understanding of the macroscopic properties of materials. We started with a couple of rather crude pictures of materials, and then we started looking at more detailed materials, but only in one dimension. So eventually we'd like to have some detailed pictures of materials, but in 3 dimensions. So we're going to turn our attention to 3 dimensions now. And this actually makes our life a little bit more difficult, a little bit more complicated. But this is the eventual objective, to describe real materials. And at this point, it's worth thinking back to one of the things that I said in the very first lecture, that the world of condensed matter physics is extremely broad and diverse. And once we understand how it is that atoms bond to each other, in ionic, covalent, hydrogen, metallic, or van der Waals bonds, you can start building up an enormous variety of different materials to study. And so it seems appropriate that we do a little bit of an obligatory tour of some of the types of condensed matter that we're not actually going to focus on, but that are out there and are worth knowing that at least that they exist. So here are just a few examples of condensed matter physics. This is the one type of condensed matter physics we are going to study, the crystalline solids, and I'll have a whole lot more to say about crystalline solids later on. The general idea of a crystalline solid is that it's some sort of periodic arrangement of atoms, and very frequently the macroscopic morphology of the crystal reflects its underlying structure, as you can sort of see in this picture. This particular picture of a crystal is quartz, silicon dioxide, in a beautiful crystal, and you can see that its structure somehow is reflecting how the atoms are put together. One can also have slightly more complicated types of crystals, whereas in most crystals, in these crystals, the atoms are held together in ionic or covalent bonds. You can have situations where van der Waals bonds are extremely important. So in this picture, this is known as a molecular crystal. What happens here is you have a lot of atoms coming together to form a molecule. They're strongly bonded in the molecule via covalent or ionic bonds, but then the molecules come together to form a crystal where it's very weak bonding between the molecules, in this case van der Waals bonds. This particular picture is a depiction of C60, 60 carbon atoms coming together to make a soccer ball shape, or if you're on this side of the ocean, it's a football shape, I guess. On the other side, football is a different shape. Anyway, so they come together to make these C60 molecules, and the C60 molecules, they're very inactive species, but they can still bond together, forming to form a crystal via van der Waals bonding. One can have situations where you have something where it's not so organized, a little bit more disordered. This is what's known as an amorphous solid. The word amorphous comes from Greek, meaning without form. Obviously, the object has form of some sort, but it's a disordered form. This is another depiction of silicon dioxide, but it's amorphous silicon dioxide. The microscopic structure here, the blue objects are supposed to be silicon, and the red objects are oxygen. Every silicon is bonded to 4 oxygen. Every oxygen is bonded to 2 silicons. And generally, we are familiar with this silicon dioxide amorphous as window glass. It has a lot of the same properties as its crystalline cousin quartz, but it is a slightly different material. We can also have disordered structures such as liquids. In liquids, there's attraction between atoms or molecules, but it's not so strong to keep it held in a permanent configuration. The atoms still have enough thermal energy to move around, and that gives the liquid its property that it can flow. You can have situations where you have partial order, where there's some amount of flowing and some amount of crystallinity, or some amount of order that remains. So this picture is what's known as a liquid crystal. The order that remains is that all of these molecules, these things that look like torpedoes or orzo, they all retain their orientation. They're all angled the same direction, and they all line up in stacks. But within each stack, they're disordered, and they can actually flow within the stack, and that's what makes them a liquid crystal. And there's a huge variety of liquid crystals depending on what type of order you retain and what type of order gets thrown away. Halfway between the disorder and disorder is also the idea of the quasi-crystal. This particular picture is what's known as a Penrose tile, named after Roger Penrose, one of the most famous mathematicians here at Oxford, one of the most famous mathematicians in the world, actually. Anyway, this is made up of two different types of tiles, these little blue objects and these little green objects, and they stack together, they fit perfectly together, and some very ordered arrangement, but in fact, all the way out to infinity, the pattern never repeats. It's an ordered but non-repeating pattern, and there are materials that have this property that are known as quasi-crystals. It was very controversial that they existed for quite some time. It has actually been determined that, yes, indeed, they do exist, and the Nobel Prize was awarded for it just a couple of years ago. There's also the idea of a polymer, which is sort of a one-dimensional, very long molecule. DNA is one that you're probably familiar with, but there's many polymers, like polyethylene, for example. And polymers have a lot of properties that are unlike other materials that we might be familiar with. For one thing, in their fluid phase, they're sort of like a bowl of spaghetti, a lot of these strands sort of all mixed in together. And they have a very non-Newtonian behavior in terms of their fluid dynamics, that their viscosity depends very strongly on the time scales that you're considering. So if you've never done this experiment with cornstarch and water, you can sort of mix up a goop of cornstarch and water that will pour like a fluid. You can put your hands in it like a fluid, but if you hit it with a hammer, it will crack. It's really impressive. The issue is that the long strands, they take some time to unentangle. So if you try to move them very quickly, they'll feel like a solid. But if you give them time to relax, they'll flow past each other. Okay, so that's just a very brief tour through some of the topics in condensed matter that we could study. Most of them we're not going to study. Mainly we're going to, yes?
So is ice a molecular crystal or an amorphous solid?
Ice is a crystal, a genuine crystal. It's an ordered crystal. Most forms of ice, there's like 20 forms of ice. Most of them are actually, the ones we're familiar with is generally a crystalline solid. It's ordered. But they're actually, there's, you make a point. Ice is a little bit different because there's some slight rearrangement of the oxygen and hydrogen atoms on a microscopic level that makes it not perfectly periodic all the time. But it's mainly a crystal. We can discuss the slight subtlety associated with ice that makes it slightly different. Yes. Okay. Mainly what we're going to study is crystal structure, crystalline solids. And here, before we get going, I have a couple of apologies. The first apology is that I'm going to have to use a lot of PowerPoint slides. And I know PowerPoint slides are annoying. It's difficult to learn from PowerPoint slides. But unfortunately, I can't draw this. All of the slides that I post are going to be on the web page. Most of them are in the book in one form or another. Hopefully that will, and the lectures will be online as well. Hopefully that will give you enough information to be able to learn the material. So that's the first apology. The second apology is, particularly in this lecture and the next lecture, we're going to have to suffer through a lot of definitions. And that's a little bit tedious, but unfortunately we need to have a language in order to be able to describe the things we're talking about. We need to be able to say, what is this picture we're looking at? Where are the atoms sitting? We need some sort of vocabulary in order to communicate. So we're going to have to just bear with that and suffer until we understand what all the words are, and then we can start moving on with the physics again. The third apology is that unfortunately not all books agree on what the proper definitions of terms are. So you will find some books that call a dog a cat and some that call a cat a monkey. So it's kind of a mess. The terms that I use are the ones that are generally accepted at Oxford. They're actually probably the most commonly used terms for certain things. I will try to point out cases where there's some disagreement as to what the terms mean or what terms should be used. But just be warned if you look in other books, and there's also caveats within my textbook as to which terms are controversial. So just be warned of that is one of the issues we have to deal with. Okay, so we're going to start with the first definition of the day. A crystal. Crystal is a periodic arrangement. Periodic arrangement usually meaning of atoms. So for example, that's a crystal. So this is a simple crystal over on the left, and then you have more complicated crystals over on the right. They can have many different types of atoms. The atoms can be in very complicated arrangements, but as long as it's periodic, it's a crystal. A very important definition, I'm actually going to give several definitions of this word, which are all equivalent. A lattice. So definition A, maybe the most useful, is it's a set of points defined as integer sums of, here's another word, primitive lattice vectors. Lattice vectors. Okay, now, here's a case, I'll explain what primitive lattice vectors are in a second, but here's a case where there's a word that people disagree on. Primitive, sometimes people drop the word altogether and they don't say it. Sometimes it's principal. Principal. Lattice is sometimes replaced by translation, and it's sometimes replaced by the word basis. That's particularly inconvenient because we use the word basis for something completely different, so that makes a real mess. Vectors is always vector. And the other thing is that some books will call lattice brave lattice instead of lattice, reserving lattice for really meaning crystal. So that makes a complete mess. Some people call a crystal a lattice and a lattice a brave lattice. Please ignore that. That's just, I mean, it makes everything incredibly confusing. Anyway, this is a good set of definitions that we will use here at Oxford. The exam committee agrees with these definitions, so hopefully it won't get too complicated. We just have to deal with it because that's the way the world is. Okay, so let me actually define, give examples of what these crystals, what these lattices are. So we did this in 1D. You have a bunch of points lined up in 1D with a distance a between them. So then we can write the positions R of the points in the lattice as n, an integer, times a. A here is the primitive lattice vector, prim lat vec. Actually, I'll frequently call that PLV, primitive lattice vector. And then n is an integer. So this is something we've seen before. We have integer times primitive lattice vector gives us the points in the lattice. Let's try one in 2D, a little bit more complicated. So the lattice points, the lattice vectors here, are integer times a primitive lattice vector a1 plus an integer n2 times another primitive lattice vector a1. The a's are the primitive lattice vectors, the PLVs. The a's should be non-collinear, so that we have something that's really two-dimensional. And the n's are integers. N's are integers, element of integers. Okay, so let's show an example of this. So here we have a lattice, and we can, a1 and a2 are the primitive lattice vectors. If we think of this point in the center as being the point 0, every point in this lattice is an integer. That's an integer times a1 plus an integer times a2. For example, this point here is 2a1 plus 1a2. Okay? And frequently we will notate r equals n1 comma n2 in square brackets to indicate n1 times a1 plus n2 times a2, like it's indicated up here, 2 comma 1 to indicate this point, if this point here is taken to be the origin. Now, I should also comment that this notation is frequently abused, that sometimes people will say the point 1/2 comma 0 or something like that to mean a point which is not a lattice point, the point which is in between lattice points. So if you want to specify this point here, you would say go 1/2 the distance of the primitive lattice vector a1. The more important thing is that the square brackets mean a point in space. And if it integers coefficients here, then you mean a lattice point. If it's not integer coefficient, then it's not a lattice point. Okay? So far, so good? All right. So far, pretty easy. We can do the same thing in 3D. 3D, we would write R equals n1 a1 plus n2 a2 plus n3 a3. And the a's should be non-coplanar, so that we're talking about something that's three-dimensional. And we can notate it as R equals brackets n1, n2, n3, like that. One thing that you should be aware of is that the choice of primitive lattice vectors, of PLVs, primitive lattice vectors, is not unique. So you can choose different sets of primitive lattice vectors, and they're perfectly OK. For example, you could choose these two things as primitive lattice vectors. You could choose these two things as primitive lattice vectors. You could choose these two things as primitive lattice vectors. The important thing is that any point on the lattice should be expressible as an integer sum of the primitive lattice vectors. OK? So far, so good? All right. First chance to win fabulous prizes. Are these primitive lattice vectors? OK, who was the first person to say? I heard. OK, no, you weren't. Someone else over here. It was you. Okay. You guys are such liars. So, all right. So, it was some voice over here. I heard it over here, but I don't know who to give it to. All right, one more chance. OK, yes, these are primitive lattice vectors. It's lattice vectors because you can get to any point in the lattice by some sort of integer sum of those primitive lattice vectors. OK, how about these? Are these primitive lattice vectors? No, they are not. So, they are not because if you add them together in all integer combinations, they miss every other lattice point. Okay? They would be primitive lattice vectors for this lattice. If I took away half the lattice points, then you have primitive lattice vectors. Okay? All right. Everyone always misses that one. Okay, every year. Okay, so a second definition of a lattice, sort of equivalent definition of a lattice, this is B, is that it is a, addition of, let's see, let me change it, is a set of vectors such that addition of 2 gives a third. Okay, and this actually, it's pretty easy to see that this is equivalent to the prior definition. If you have n1 comma n2, both of those being integers, so it's an element of the lattice, and you add it to n3 comma n4, both of those being integers, so it's an element of a lattice, you get n5, n6, and those are then integers also, and therefore an element of the lattice as well. A third definition, C, is that a lattice looks the same from viewed from any lattice point. Okay, so for example, if I sit myself here, so this thing is a lattice. If I sit myself here and I view the environment around me, I say, okay, there's a point to my left, this distance, there's a point to the right, the same distance, there's a point up right, up left, down left, and I can measure the distances, I can measure the angles. And if I sit here, another lattice point over here, it has exactly the same environment, a point to the right, a point to the left, a point to the upright, up left, down left, exactly the same distances, exactly the same lattice, exactly the same angles. If this is true for every one of these points, then what you have is a lattice. Okay? So for example, is this a lattice? No. Who's it? I heard that's over here. Who is it? Was it you or you? No, okay. All right. Fight for it. All right. Okay. So I have to give out some of these. I have like 6 of them here. All right. So okay, this is not a lattice, and there's several ways to see why it's not a lattice. So first of all, from the first definition, are there primitive lattice vectors which we can add up in all integer combinations which would give exactly these points and only these points when summed together with integer coefficients? Well, there aren't, but it may not be so obvious to see that that's true, that you can try coming up with 2 primitive lattice vectors, A1 and A2, and seeing if we can come up with these points and only these points. You can't do it, but it's much easier to use some of the other definitions, like this one. We should have, if we sort of think of this point here as being 0, then we have this lattice vector here and this lattice vector here. When you sum them together, they should give a third lattice vector, But if you sum these two together, you get a point in the middle of this hexagon, and it's not there. That's not one of the points in our set. So this is not a lattice because you can't sum two things together and always get a third. The third definition is that the environment of R, the environment of all points should be the same, and the environment of R is not the same as the environment of P. R has another point to its south, whereas P has a point not to its south, but to its north. So P and R are inequivalent points. P and Q are equivalent. Okay? So even among the professional literature, people will refer to this thing as the hexagonal lattice, and that's just wrong. It's not a lattice. You shouldn't call it the hexagonal lattice, although people always do. So be warned about that. I know this is horrible to be giving you all these caveats that people say these things wrong all the time, but it's just true, they do. Okay, so let's go on. Fact. Any periodic structure is a lattice of repeating motifs. Okay. Any periodic, this is just a fact, any periodic structure is a lattice of repeating motifs. So here's my, this is the same picture in the book. I just like these things. They're armadillos, I guess. So you have this periodic structure of armadillos. And in fact, if you take a lattice here, it's a triangular lattice made up of a bunch of triangles. It's a nice lattice. And you replace each of these points with an armadillo, you get the whole periodic structure. So I've drawn it as lattice times the repeating structure, which is the armadillo. Well, what about this? This is certainly a periodic structure. So can we see how this thing is actually a lattice of repeating motifs? Okay? I claim that it's a triangular lattice, this triangular lattice of blue dots, times this repeating motif. And that might not be so obvious to see, but let's see if we can make it obvious. So first what I'm going to do is I'm going to put a big red dot in the middle of each vertical edge. Okay? So here's a big red dot, here are big red dots, and now it's looking a little bit more likely that, first of all, these big red dots are clearly forming a triangular lattice, just like this triangular lattice down here. Now let's make it a little bit more obvious by putting a green diamond around this repeating motif, and you can see that, in fact, if I stack together these green diamonds, each one of them centered on these big red dots, it will reconstruct the entire honeycomb, this thing that people call the hexagonal lattice that isn't a lattice. So it should be called the honeycomb, I guess. All right, is that clear? Okay, good. Good. So far, so good. So that brings us to another very useful definition, which is a unit cell. Unit cell equals a region of space. It's the repeating motif. It's the region of space which, when repeated and stacked together, and sometimes we use the word tiled, meaning repeated. Tiled means repeated and stacked together, reconstructs the full periodic structure. We used this term unit cell previously in one dimension. Now we can just use it in general dimension. So this green diamond would be the unit cell for this repeating structure. Okay? And let's see if we can do another one. Here's our armadillos again. So we have a unit cell which contains one armadillo. We can stack them together. What's important about unit cells is that they have to stack together with no space. They should be like bathroom tiles. They should fit together exactly with no space between them. Another definition which is useful is a primitive unit cell. Unit cell equals a unit cell containing exactly one lattice point. Exactly one lattice point. So, for example, in this picture, this would be a primitive unit cell because it contains one big red dot, and that's the lattice point. And okay, so we can't see the lattice points in here, but if you remember where they were in those blue pictures, the armadillo is sitting on top of the lattice point, so each unit cell contains exactly one lattice point. I guess here's another case. Here's a nice lattice. There's a primitive unit cell because if you can tile all of space with it, you put them together, tile all of space, and each unit cell contains one lattice point. However, one should be warned that the primitive unit cell is not unique. You have different choices as to what you want to use for your primitive unit cell. For example, here's a lattice written 4 different times, and you can choose primitive unit cells to be any shape. So you can choose them this shape, this shape, this shape, this shape. As long as they fit together and tile all of space, you have a very nice primitive unit cell. Okay? Some of them are more convenient than others. One should be warned that something like this is also a good primitive unit cell. And that's a little less obvious that contains exactly one lattice point. But you have to think about the things that are partially enclosed in the unit cell, like this guy, as only counting as theta of the full circle. And this one counts as theta of the full circle. This one is pi minus theta of the full circle. This is pi minus theta of the full circle. And if you collect all those pieces of the lattice point, you put them together, you'll get the full 2 pi. Okay? So it's one lattice point, but it's broken up into 4 pieces. Okay? It's one lattice point broken into 4 pieces. Maybe this is also a good primitive unit cell. This is a lattice point more obviously broken into 2 pieces. You assemble them together, you get the one lattice point back. And this one is a simpler unit cell, which is maybe easier to see that contains exactly one lattice point. Another definition, I know we have a lot of these. Conventional unit cell. Unit cell equals conventional, it's convenient. A unit cell, a non-primitive unit cell, non-primitive unit cell that is convenient which usually meaning orthogonal axes, orthogonal axes. Did I spell that right? I think so. So for example, here we have a triangular lattice and a conventional unit cell here with orthogonal axes rather than a primitive unit cell. So how many lattice points are in that? Someone up there. Who was it? Someone way back there? All right. I believe you because you look honest. Okay. So, yes. Okay. Another definition. Maybe start over here. A Wigner-Seitz cell. Wigner-Seitz cell. Wigner was a very important physicist, if you haven't run into his name already. Seitz was, well, he was less important, but also important. The region around a lattice point closer to that lattice point, lat point, than to any other. Okay, so you have a whole bunch of lattice points. You would like to find the region around one lattice point that is closer to that lattice point than to any other lattice point. And there's a way to do this, which is the Wigner-Seitz construction. Wigner-Seitz, how you find that region, construction, which, I will explain this construction. It's easier to describe it than to write it out. But I'll write down use perpendicular bisectors. So let's see how we do this. Okay, so here's a lattice, and I've labeled one of the points of the lattice black. We'd like to find the Wigner-Seitz cell of that lattice point. In other words, what is the region of space which is closer to that black lattice point than it is to any of the blue lattice points. Okay, how do we do that? Well, you pick a neighboring point, like this one point up here, and you put down a perpendicular bisector, this red line. Okay? Now, everything on the lower side of that red line is closer to the black point than it is to the blue point labeled 1. Right? Definition of perpendicular bisector. Now, let's do that with another point over here, this point 2. And now we have this vertical perpendicular bisector, and everything on the left-hand side of the vertical line is closer to the black point than it is to the blue point labeled 2. And you do the same thing for 3, and 4, and 5, and 6, and all the way around until you wall off a region, and everything in that region, which I've now colored green, is closer to the black point than it is to any of the other blue points. Okay, is that clear how that works? Okay, good. So then you have this nice region, which is a Wigner-Seitz cell, and it turns out that the Wigner-Seitz cell is primitive unit cell. Primitive unit cell. Well, first of all, it obviously contains only one lattice point, so that's good. It tiles space because you can put a Wigner-Seitz cell around every point in space, and obviously every point in space is in the Wigner-Seitz cell of some lattice point. Whichever lattice point is closest to you, you're in that Wigner-Seitz cell. And so it tiles space and it encloses one lattice point, and each one of these has the same shape, so it's a nice primitive unit cell. Okay, good? Everyone happy so far? Okay, now I'm going to, I think this is not on the syllabus, so you don't really need to learn it, but it's pretty cool. Known as a Voronoi cell. Did I spell it right? Voronoi cell, which is a Wigner-Seitz cell for a non-lattice, collection of points. So imagine you just have a bunch of points, say in a plane, and you wall off the region which is closer to one of the points than to any of the other points. And this concept of a Voronoi cell shows up not only in physics, it shows up in chemistry, biology, epidemiology. It shows up very heavily in computer graphics. It shows up in just all over the place, including pizza delivery. So I'm going to explain to you why it's important for pizza delivery. And you'll realize why the Voronoi cell is such an incredible thing. So okay, so this program you can click, it's linked to on my website. So imagine this blank sheet here is a map of Oxford. Nothing's written on it yet. And you own 2 pizza shops, okay? And one of them's in North Oxford, we'll put it here, and one of them's out in Cowley, it's over here. So that blue line is the perpendicular bisector between those 2, okay? Now, if someone calls you up and says, I want a pizza, if they're in this region, they're closer to this red point, so you have the guy in North Oxford deliver. Whereas if it's down in this region, well, it's closer to this point, so you have that guy deliver. Now, you're making a lot of money, so you buy a couple more pizza shops. So let's put in a couple more. 1, 2, 3. Okay, you have a bunch of pizza shops. And now, these are the Voronoi cells of each of these red points. So this region here, everything inside this region here is closest to this red point. That's its Voronoi cell. So if someone calls within this region, it's serviced by this guy who's closest to them, and so forth and so on. You can keep going on and on and on and adding points, and these cells indicate that cells always wall off the area which is closest to that red point. And you can kind of guess that there's going to be millions of applications of the idea of the Voronoi cell in lots of different areas of science, including pizza delivery, which should be a science by now. Okay. All right. So that's all we have to say about Voronoi cells. So next, the word basis. This should not be confused with the word basis that we had when we talked about primitive lattice vectors, and some people call them primitive basis vectors. That's not this. This is why we do not use the word basis when we talk about primitive lattice vectors. We don't call them primitive basis vectors because we're going to use the word basis here. Sorry about that confusion. Okay, so basis is a description of objects in the unit cell, with respect, R-E-S-P-E-C-T, with respect to our reference lattice point. Okay, so for example, oops, okay, there. So here we have a periodic structure. I've put the lattice, the reference lattice point, I've drawn it blue in each of these unit cells, and then you'd have to describe everything that's in the unit cell referenced to that one lattice point. So you would say there is an armadillo sitting on top of your blue dot. Okay, maybe that's not so useful. Let me do a more physics-oriented one. So here's a crystal here made up of two different types of atoms, the large light gray atom and the small dark gray atom. Okay? The black points are reference points that give me the corners of the unit cell. So here's a unit cell, and here it's just been blown up a little bit so you can see it a little bit better. So here we have a unit cell, next unit cell, and if you stack the unit cells together, you reconstruct the whole crystal. Now, a basis is that we should list off all of the objects in the unit cell referenced to the reference lattice point, which we call coordinate 0, 0. So we would say, for example, there's a large light gray atom at position a over 2, a over 2 here with respect to this point 0, 0. Then there are small dark gray atoms at positions a over 4, a over 4, 3 over 4, a over 4, 3 over 4, 3 over 4, and a over 4, a over 4, so, 3 over 4. So once I've given you all of this list of where all the objects are in the unit cell, what the objects are, and what their relative vector is with respect to the reference lattice point, I've then given you a basis for the crystal. Is that clear? So if I tell you the lattice and I tell you the basis, I've told you the whole crystal. So this is the language we need in order to describe the whole crystal. Now, sometimes it is useful, okay, so here it's useful to take the reference lattice to be coincident with some atom. So here's a crystal made up of red and blue objects, red and blue atoms. Now, you can take a unit cell that looks like this. It contains one red atom and one blue atom. But what people do more often is they put the unit cell with corners on the red atom. Or they could have chosen blue, but in this case, we're going to choose red. Then we would say our basis is the red atom is at the 0, 0 position of the unit cell, and the blue atom is a distance 1/2 in the A1 direction from the red atom. So it's at position 1/2, 0. Now note, it's really important not to overcount the red atom. So you don't say that there's a red atom at 0, 0, and another red atom at 1, 0, and another red atom at 1, 1, and another red atom at 0, 1. That would be counting 4 red atoms, and there's only one red atom in that unit cell. It's divided up into 4 pieces, but you only have to list it once. It's at 0, 0, and then it's implied that if it's at 0, 0, it's also at all the other pieces. It's other, it's quarters, the way it's divided up. If it's one piece of it is here, the other pieces of it are going to be there. So you don't overlist it. Is that clear? List it just once. It's something people frequently make mistakes on. All right, so now we can move on to what we're finally building up to, 3D lattices. 3D lattices. So this is an important statement, maybe the most important statement I will make all day. You will not need to know by the decrees of the exam committee, you will not need to know about lattices in 3D. In 3D, where axes are not orthogonal. Why? Well, because then you won't have anything to learn next year. No, I mean, the reason is it's just because it gets a lot algebraically more complicated, and it was sort of just agreed upon by the exam committee that in third year we can, all of our 3D lattices, just to prevent us from getting just knee-deep in all sorts of algebra of angles, we're just going to stick with orthogonal axes in 3 dimensions. And I think that rule has never been broken as far as I know. So I've been told this is a hard and fast rule, so you can stick with it. I hope it stays true. So the simplest lattice in 3D, cubic lattice. We colloquially call it a cubic lattice, but it's probably more properly called simple cubic, or primitive cubic, or cubic dash p for primitive. And you probably know what this looks like. It looks kind of like this. The unit cell for this, unit cell equals a cube. Unit cell equals a cube. And it looks like this. How many atoms are in that How many lattice points are in that unit cell? One, okay. Everyone's yelling out, so I don't know who to give this chocolate to. I'll have to eat it myself. All right. So, yes, it's one lattice point in that unit cell. So that's a primitive unit cell. And it's 1/8 times all of the 8 corners. Each corner is 1/8 inside the unit cell. We can write down the lattice points in a more proper way, that R equals UVW times the lattice, the edge length A, where UV and UVW are all integers. Okay? Now, we were told at the beginning that we should be able to write the lattice points as integer sums of primitive lattice vectors, so we can choose A1 equals A times 1, 0, 0, A2 equals A, 0, 1, 0, and A3 equals A times 0, 0, 1. And these are the primitive lattice vectors, PLVs. Okay? Good. There is yet another word that's useful to know, is the idea of a coordination number. Number, which is usually called Z, which is the number of nearest neighbors. So what's the coordination number of this cubic lattice? Someone said 6. Who was the first person to say 6? It was over here. It was, okay, I trust you. I believe you. One of these will be yours. Right. Yeah. It still tastes good. It's good chocolate. So actually, you know, the woman who lived, the oldest recorded human lifespan, Jean Calmette, she lived 124 and a half years old. She ate 1 kilogram of chocolate a week. It's true. It's on Wikipedia. So, all right. So actually, the simple cubic lattice, although it's, this is what it would look like if you put atoms on the position of each of the lattice points. It's a cube, obviously. Although this is a very simple lattice to describe, it's actually extremely unusual in nature. Of all the materials, all the atoms on the periodic table, only one element actually takes this simple cubic arrangement. The element is polonium. And for one more, who discovered polonium? Someone over here. Was it you? I believe you? Okay. It was Mary Curie. And polonium was named after her home country of Poland. Have to mention that because Mary Curie is one of my heroes. All right. So, and the reason why this is so unusual, you have to sort of think about stacking spheres. If you ever try to put like tennis balls in a box or something, you'll realize they really don't like to stay in this position. They really want to fill that hole in the middle. There's a lot of extra space in that hole in the middle, and someone will fall into that extra hole. Another way to think about it is that, you know, there's a bonding force that wants to get these atoms really close to each other, or fairly close to each other. If you sort of think of them as hard spheres that are trying to attract each other, that it's not really going to like to leave that great big hole in the middle. Something's going to want to fill that hole. So that's why the simple cubic lattice is very unusual among pure elements. So there are some variants on the simple cubic lattice that we need to know. Tetragonal lattice, which means axes perpendicular, 2 edges equal. So let's draw a picture of that. So here's simple cubic, here's tetragonal. 2 of the edges are equal, 1 edge is different, and the other we need to know is orthorhombic, which is axes perpendicular, no edges equal. Okay, so there we go. Simple orthorhombic, all edge lengths different, but at least all orthogonal. Now, although simple cubic is very unusual in nature, there are things that are based on simple cubic that are quite common. So you do need to know about the simple cubic lattice. So let's go back to this picture here. Remember, it's very convenient if you have more than one type of atom to put the reference lattice, the reference atom at the lattice point, and then another atom you can reference, you can give a basis by giving its position with respect to the reference lattice point. So a very important structure is the so-called cesium chloride structure, named that way because the material cesium chloride takes that structure, obviously. Cesium chloride, it's extremely ionic material. Cesium gives up its electron very nicely, and chlorine is extremely electronegative, so it wants to take that electron, and so you get a nice ionic bonding. So the definition of cesium chloride structure is cubic lattice with a basis, simple cubic lattice, or p cubic, primitive cubic lattice with basis, where we put the cesium at position 0, 0, 0 on the lattice point, and the chlorine at position 1/2, 1/2, 1/2. That's in the middle of the hole that we had in this picture here. So the chlorine is going to fill that hole. So what we get is something that looks like this. We get the cesiums on the corner of the unit cell and the chlorine sitting in the center of the unit cell. Okay? Now, you might think of it this way, as having cesiums on the corners of the unit cell and the chlorine in the center of the unit cell, but that's kind of arbitrary that we chose it that way. Because so here's another picture of the same structure. The cesiums are white and the chlorines are green here. So here's the unit cell we were just discussing with cesiums on the corners and chlorine in the center. But one could just as well have chosen this as the unit cell with the chlorines on the corner and the cesium in the center. So what we really have is two interlocking simple cubic lattices. One of them is made up of the cesiums. One of them is made up of the chlorines. Okay? And here's a animation that's supposed to show that. So that's cesium chloride. There's the cesiums. Here's cesium chloride again. And there's the chlorines. Each of them is a simple cubic lattice, and they're sort of stuck together. So this type of structure, the cesium chloride structure, is actually quite a common structure in nature. Now, we can do something else, which is to consider pure cesium, which is a very similar structure, pure cesium structure. So we have, so it's a cubic P lattice, but we, maybe I'm going to put this in parentheses because we're going to say that's a lie in a moment. Cesium, we're going to put the cesium at 0, 0, 0, and then another cesium at 1/2, 1/2, 1/2. Okay? So all we're going to do is we're going to take that cesium chloride, and we're going to get rid of the chlorine in the middle and replace it with another cesium. Okay? So we can think of it as simple cubic with the basis, where the basis is a cesium at 0, 0, 0 and a cesium at 1/2, 1/2, 1/2. Now, this is actually itself a different type of lattice. This is an important type of lattice that we're going to be studying, which, well, it's known as the body-centered cubic lattice. Make sure I don't miss anything. Body-centered cubic lattice. Also known as cubic -I. So the word body-centered, it's not, it sounds like something out of yoga or something, but it's actually, the idea is that you've put another point in the center of the body of that cube. I is from German, innerzentriert, which must mean something, any German scholar, it's something like, means in the center of the body or something, I don't know. Anyway, so I'm going to claim that the environment of all of these points is exactly the same, so this is actually itself a lattice. So let's see how this works. This is the unit cell of the body-centered cubic lattice. How many lattice points are in the body-centered cubic lattice? All right, I didn't. Okay, it's 2. This is the conventional unit cell of the body-centered cubic lattice. We take the conventional unit cell to be the cube again, just because it's more convenient to do so. There's 1 in the center, obviously, and then we have the 1, which is divided into 8 pieces in the corners. Now, there's a convenient way to describe these three-dimensional structures, which is to use what's known as a plan view. A plan view comes from a sort of architectural term where you look down on the thing from the top and you draw the heights. You indicate the heights of all the things that you see. So if you're up in a helicopter and you're looking down on this conventional unit cell, you would see 4 things in the corners, and you would see 1 in the center, and then you label the heights. So this one is labeled with height a over 2, and then down here it says unlabeled points are at height 0 and a. So this one's at 0 and a, 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 and this one here is at height a over 2. Okay? If you put atoms together in this body-centered cubic structure, they would look more like this, and it's actually, it's filling up much more of the holes of the lattice this way. It's much more efficient sphere packing, and there's quite a few materials that actually take this body-centered form. Sodium, lithium, iron, potassium, there's many, many, many more. So what is the coordination number? 8. Who's said it? Who's over there? Okay. Yeah, okay, 8. It's 8. So if you pretend you're the guy in the middle here, then you have 8 neighbors, each one of those 8 neighbors. What's less obvious is that if you happen to be one of these guys in the corners, you also have 8 neighbors. Okay? Every point here is identical. Maybe I'll show it here. So here's the conventional unit cell, like this, and here's the point in the center. Now you could just as well have chosen this point to be the center of a cube, and then we would have this cube with this point in the center. Okay? So again, remember that this is really 2 interlocking simple cubic lattices. When we were thinking about it as being cesium chloride, there were 2 interlocking simple cubic lattices. So if we choose this point as the center, then the yellow ones make the cube around it. If we choose this one as the center, then the red ones make the cube around it. Either way, it always has 8 nearest neighbors. Okay? The last thing, I think we're out of time, we'll pick up next time, and we'll prove that this thing is actually a lattice by the definitions of lattice that we gave at the beginning of the day. All right, I'll see you tomorrow.